This is an attempt to use things like tree rings and ice core data and stuff like that to kind of go back to an earlier epoch. So this is an attempt to reconstruct global temperatures to about 1000 AD. This has generated a lot of controversy because people that don't like global warming talk about all the uncertainties in this type of calculation. But such as it is, these calculations have not been done by me, and I'm just sort of showing them. This is what seems to be suggested if one tries to reconstruct temperatures back 1,000 years. But this period of warming that we've seen in the last few decades, seems to be unprecedented. But that's a difficult one. So I want to come to an area. This is where I can work in, which is this whole area of modelling. So I'm going to show you another animation of the world, but now not from a satellite, from a computer. So this is looking inside a computer model, and this is again showing precipitation, so liquid water, if you like. And again, you can see the sort of complicated weather patterns are being generated fairly sort of realistically. As I say, the reason, so just to say once more, the reason we use these types of models is that to understand climate change, this interaction between CO2 is a pretty well mixed gas. So the 381 parts per million don't vary. If you measured CO2 around the world, you wouldn't see big variations in CO2 concentration. It's fairly well mixed. But water vapor and water content are highly inhomogeneous. And so to try to really understand properly the interaction between increasing levels of CO2 and increasing levels of water, we need these kind of realistic models.
Can I ask you,
yeah.
What are these models? Are these sort of ability models?
I'm going to talk about that. Yeah, just let me just. That's just coming up. Oh, here they are. Yeah. So here's my. So yeah, people think these models are just my prejudice about what the weather's going to. No, I know you're not saying that, but this is what the public think, or they're just a kind of glorified Sony workstation game, type of thing. Well, no, they're not. They're based on this guy here. Now he didn't know anything about global warming, but. But his physics is put into these models. This is a slide which I showed. Now, the public don't understand this equation, of course, but I point out. And by the way, I showed this because
This Stokes?
Stokes, yeah.
This gentleman, is it Stokes?
This is Stokes. I gave this talk in Ireland. Stokes is an Irishman. I've yet to be invited to France to give a talk. If I was, I would have a picture of Navier, no doubt.
Consider yourself invited.
I just explained. I mean, this is basically an expression of Newton's law. I mean, I talk about Newton's law. If it's an English audience, I talk about hitting a cricket ball with a cricket bat or something, and the fact that you hit it with force and off it accelerates. So this is the same law, but applied to the whole atmosphere. Now I try to liken this to. So I say this is a fantastically beautiful equation, which I think it is, and I liken it to a work of art. We had a talk about the connection between science and art. So this in my view is a work of art. But the piece. But rather than sort of liken this to a Renoir or a Matisse or something like that, I liken it to this Russian doll here. And the reason I liken it to a Russian doll is that by the way, this is a rather special Russian doll because it unpacks not into just a few Russian dolls, but even more Russian dolls, and those unpack into yet more, and yet more still, and yet more still, and so on, and so on. And the reason for saying that is, as you all know, that this is a partial differential equation, and if you actually want to solve it on your computer, you have to first of all do a similar unpacking, if you like, into ordinary differential equations. And the problem is that this is beautifully elegant, but and the beauty kind of belies its complications because it describes scales of motion from the very largest scales on the planet, tens of sort of jet stream meanders of wavelengths of tens of thousands of kilometers, right down to little sub-millimeter scales. So this Russian doll, the biggest Russian doll of my Navier-Stokes equations has about a 10,000 kilometer let's say height or something, and my smallest is less than a millimetre. And moreover, these equations are non-linear. A couple we use here. And what that means is what I say, that what it means is if you jiggle this big guy, or this big dog, I mean it will jiggle all the other ones down in turn. But conversely actually, if you jiggle the small ones, they'll jiggle the back ones, the big ones. So you have this sort of energy being propagating backwards and forwards across scales, which means that you can't just look at this one or this one or this one in isolation. You have to consider the whole thing together. And herein lies, the problem that even the world's biggest computers aren't big enough to represent all those scales from tens of thousands of kilometres down to little ones of less than a millimetre. So what I have to do is truncate. I'm interested in these. I definitely am interested in the very big. I want to know what global warming is, and I want to know what this one could be the size of North America or Europe. This one could be.
How do you find the scales? How do you find the scales?
Well, these are done by actually, you're all familiar with spherical harmonics. What we actually do is decompose the. Actually, coming back to this equation, we actually project this onto a spherical harmonic basis, and so the differential equations are differential equations for the coefficients of the spherical harmonics. And there may be hundreds of there are hundreds of such spherical harmonics.
But actually this is taking place on a sphere.
This is taking place on a sphere. Yeah, I'm sorry, this is all global, these are global models.
So the number squared is this Laplacian of the sphere.
Exactly,
Yeah.
that's right. And we have to do it at each level as well, so there are potentially levels going from the ground up into the mesosphere.
Yeah, because you're
So actually, we end up with, we typically end up with 10 million in these models. Well, let me just come. So we can't, even the biggest computers can't represent everything down to sub-millimetre scale, so we actually have to truncate. So we get rid of a load of these, and we get rid of some more, and we get rid of some more, and maybe get rid of some more. And now we've got, let's say, down to about 100 kilometre. So that would be a typical minimum scale in today's global climate models. And typically, bearing in mind, I showed the momentum equation. We also have one for temperature and water and maybe other constituents that you're interested in the atmosphere. So typically we have about 10 million ordinary differential equations that are actually, in these global climate models, coupled nonlinear differential equations. But the problem is that, you can't really neglect altogether the stuff that you have decided, you haven't got a big enough computer to represent explicitly. So we have to do something, and I've represented the what we do by this rather inelegant tin can. So this is not a beautifully handcrafted Russian doll, it's just an ugly old tin can. And this ugly old tin can represents what I'm calling simplified approximate formulae. I mean, the word is often used parametrization and parametrizations to describe the bulk effect of motions, of scales of motion that we can't resolve. Now, clouds, you see, are part of that. I mean, individual clouds have scales of maybe a few hundred meters up to the biggest thunderstorms, maybe a few tens of kilometers. So what we try to do is apply, if you like, the ideas in statistical mechanics to come up with kind of simple, diffusive type bulk formulae which might describe the net effect of all these motions that you can't resolve properly. The problem actually is that the methods of statistical mechanics don't really work, because you don't have a scale separation between the things that you are resolving explicitly and the things that you parameterize. So in statistical mechanics, you're only interested in macroscopic phenomena, and the jiggles of atoms are down at the micro scale. Whereas we're trying to apply the same techniques to kind of get simple formulae for things that we can't resolve explicitly, but they're not scales separated from the. So this is a real one of the big issues in scientific uncertainties, that because we're limited by computers and because a lot of the important things that determine climate, as I say, the water, how water is sucked up from the ocean and how it's transported around